Okay, so we're gonna introduce with the function of the springs. Okay, so we're gonna discuss the different type of springs, such as the compression spring, extension spring, and the torsional spring. Okay, so basically for the springs, its function includes like the exert force, or provide a flexibility, and store or observe the energy. Okay, so it would be major functions for spring. Okay, for spring. Okay, so the first compression spring that we're gonna introduce is the helical spring. Okay, the helical spring. Okay, so the helical coil spring with round wire, equilibrium force at cross sections anywhere in the body of the spring indicates direct shear and torsion. Okay, so the helical spring is subject to the compression force. Okay, compression force, right? If we just cut section anywhere, for example, cut section anywhere, and we fix on this cross section here, so there must be a force, right? Which is parallel to this cross section, and the movement of the force create a moment, or say create a torque. Okay, create a moment or create a torque. Okay. Okay. Therefore, for this section, this cross section, we have to focus on two stresses. Okay, torsional shear and direct shear. Okay, torsional shear and direct shear. Okay. Therefore, for this maximum stresses, which includes the torsional shear and the direct shear, right? Torsional shear, direct shear applied to this cross section. Okay, and then we can substitute this tau max, the maximum shear, tau, and with the torque equals to Fd over 2. The D is the mean diameter, okay, the mean diameter of this torsion, of this spring, okay, and the radius equals to the lowercase d divided by 2, and the lowercase d represents the wire diameter, okay, the wire diameter. And the polar moment of inertia equals to pi d power of 4 divided by 32, and the cross-section area equals to pi d squared over 4. Therefore, we get the maximum shear stress, right? So we can just plug in those like torque, the radius, and the J and the A, right? So we get the shear stress, right, at anywhere located at the cross section, okay, the cross section, okay, okay. So and then we can factor out the torsional stress. Okay, we can factor out the torsional stress. So we can just rearrange this shear stress that we already derived from the previous slide, right? Right? So we can just fraction out this torsional stress, right? And we can rearrange the parameters, which is the 1 plus the d over 2, the capital D. Okay, as what I mentioned, the capital D presents the mean diameter of the spring, and the lowercase d presents the wire diameter. And then we define an index called the spring index, C equals to the capital D over the lowercase d, which can be used to evaluate the coil curvature effect. I'm gonna discuss this later. Okay. And now we have to define the shear stress correlation factor. Okay, the shear stress correlation vector Ks. Okay, Ks. So suppose if the spring wire is a straight wire, right? Straight wire, and just we apply this stress, right? This maximum stress. We need a correlation vector. Okay, we need a correlation vector to evaluate its actual shear stress. Okay, Ks equals to 2C plus 1 over 2C. Okay, 2C plus 1 over 2C. If this C, the spring index here, C is less than 4, that's mean this wire for this springs is too bent. If the C is greater than 12, that means this spring is gonna self-individual pack. Okay, self-individual pack. So you can think of what's the situation is if this is the spring index is is less than 4. What's the situation should be? That's mean the D is the capital D, the mean diameter is smaller, right? It's smaller, right? It's smaller. Therefore, in this case, this spring may be like this, right? So it's easy to bend it, right? It's easy to bend. Okay, and if this spring index is greater than 12, that means what? That means this D, this capital D, is larger, right? So this will be the case of the the C is greater than 12. Okay, greater than 12. Okay. Okay, so the maximum shear stress for helical spring, we can apply this correlation vector, right, to evaluate its real shear stress. Okay, so if we look into the cross section of the helical spring, any location, so we see for this pure torsional shear stress, right? So it's applied to a torque, right, on the surface. So we already know from the materials mechanics course, the maximum shear stress is located at the surface, right? Located at the surface with the torsional with a torque applied to it. Okay. 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 And meanwhile, there's the direction shear, right, parallel to this cross section of the wire, right? So for this equilibrium shear stress equals to the torsional stress plus the direct shear. Okay, so we got this tau S here. Okay, so when the wire is bended in form of coil, the length of the inside fiber is less than the length of the outer fiber. Okay, because of this, we call this the coil curvature effect. Therefore, we have to use the correlation vector. Okay, we mentioned previously the correlation vector Ks. Okay, and this curvature effect, coil curvature effect, result in the stress concentration at the outer ring of the coil. Okay, therefore the shear stress in the fiber after stress concentration vector tau will equals to this term. Therefore, define the correlation vector, stress concentration vector, or we can say it's the correlation vector. Okay, or we can call this it's a correlation vector. Okay. Okay, so curvature effect, especially it's used only for the fatigue. Okay, fatigue. Okay, so stress concentration type of effect in the inner ring due to curvature and can be ignored for static. This curvature effect can be ignored for static ductile condition due to localized core working. And this effect can count for effect by Ks by what factor, or the Berger-Strausser factor KB, which count for both direct shear and the curvature effect. Okay, so what we need this Ks, this coefficient, because of the curvature effect, right? Because the inner ring, the inner fiber, or say the outer fiber, right? So they have the different stress concentration due to the different lengths of the the inner and the outer fiber. Okay, I'm gonna actually explain this later, but at this moment we're gonna say, due to this effect, the stress concentration inner at the inner and the outer fiber, right? So we have to take into account the other factors, KB or KW, okay, for the direct shear and the curvature effect, okay, from these two scientists, okay, to define these two vectors, KW and the KB. Either way, you can use KW or KB, and in this course, we're gonna use only the KB instead, okay? So we're gonna only use the KB. Of course, you can use KW, that's no problem, okay? So we can replace the KS. So therefore say, the KS, that's what I mentioned previously. Okay, so for the KS, well, it's for the we don't consider the curvature effect. Okay, suppose there's no curvature effect. Okay, case is fine. However, for this helical spring, there's a curvature effect with a different stress concentration at inner and outer fiber. Therefore, we have to use the KB or KS, okay, to replace KB, KW, right? To replace the KS, okay? Therefore, can rewrite this stress equals to KB times this term, okay? And this term, this stress can be used to predict the maximum shear stress, okay? Okay, and canceling the direct shear to isolate the curvature effect. So if we're gonna think of the curvature effect to isolate the curvature, if we just isolate the curvature effect, we can define the factor Kc equals to Kb divided by the Ks, right? So we're gonna isolate it. This okay, direct shear, okay. Okay, so in this case, we're not gonna use the Kc usually, so we're gonna use the KB most of the time, okay. Okay, so what's the curvature effect is? Okay, suppose we look at the ring, the fiber of the each helical spring, right? So we can just stretch it, right? We can just stretch the helical spring to a straight line, right? To a straight line. Okay, and we can cut the any position of this ring, this wire. Okay, this wire, spring wire, or say the spring coil. Okay, and we just stretch it and extend it. Okay, to a straight line, a straight line. So for this inner ring, we get the straight line, right? AB. Okay, for this inner ring, and whose length equals to this term. Okay, so inner length equals to the n, the number of coil, times the circumference. Okay, and we get the length, the inner length of the spring coil. Okay, similarly, we can get this outer length equals to pi d at n times the pi times the capital D plus the lowercase d, right? So we get this outer length here. So obviously the two lenses are different, right? Are different. Okay, that's the reason why the curvature effect occurred. Okay. So there's some text to explain what this curvature effect is. So okay, so I'm gonna skip this a little bit, but basically the inner lens AB be smaller compared to the outer lens CD, right? AB smaller than AC that we already explained, right? Previous slides. And the shear strength at the inside of the spring will be more than the shear strength at the outside of the spring, right? Therefore, this shear strength gamma I will be greater than the gamma O or gamma naught. Okay. Hence, for a given wire diameter, a spring with the smaller diameter will experience more differences of the strength between outside face and inside face compared to its larger counterparts. Okay. The above phenomenon is termed as the curvature effect. So more is the spring index, the lesser will be the curvature effect. Why? So with the higher value of the spring index, that's mean we can just reduce the curvature effect. Right? You can reduce the concentration, stress concentration. Okay, think of why. For example, like the suspension in the railway, the carriages use the helical springs, and this springs has the large wire diameter compared to the diameter of the spring itself. In the case, the curvature effect will be predominantly high. Okay. Okay, so the easiest way to explain this curvature effect is, suppose we have this straight line, we have the same length with the inner and outer ring. Suppose it's like a solid rod, right? So we already learned this torsion, right? This torsion in the materials mechanics course, right? So when this is a solid rod, we apply a torque T, and there's a angle gamma, the shear trend, right? And at this cross-section surface with the twist angle phi, right? The twist angle phi, okay? And we can define the shear trend gamma equals to rho, the radius, times the twist angle over the length of the rod, right? And for this spring coil, the inner ring, oh, sorry, this is wrong typo. This should be outer, sorry. Okay, so the length of the inner ring is shorter, right? Compared to the outer ring, right? Okay. So we get the difference between the Ri and R naught, right? I already mentioned this previously, right? So if we have a shorter length, okay, it's the inner length, right? So if we have a shorter length here and we get a higher shear strength, right? We get a higher shear. That's why we mentioned previously that the shear strength, right? This inner shear strength is greater than the outer shear strength, right? Okay, so that's the explanation for this curvature effect. It's because the difference between the inner and the outer lens. Okay, and there's a stress concentration. Okay. Okay, so now we're gonna discuss what is deflection of the helical spring. Okay, so if you guys still remember the energy method, it's called the Cartesian theories. So we can get the energy if we take the derivative of the energy with respect to the factor Q. It can be force or moment, and we can get the deflection. Okay, we can get a deflection. I still remember this. Hopefully, you can still recap the content of the this theory. Okay. Okay, so let's just recap it a little bit. So for the Cartesian theory, okay, suppose we have the cantilever being here, okay, right, and we apply a force F. There's a deflection, or we can say the theta. Okay, so from the beginning, from the physical fundamentals, that is the work equals to F dot S, right? Okay, and the du, the derivative of the energy equals to dF times the delta. They'll say the delta equals to the du over dF, right? So the delta will equals to the partial u, take the derivative with the partial f. Okay, so this is the Cartesian theory, and similarly, you can get a deflection as a theta. Okay, as a theta. Okay, as this angle, right? Similarly, the du equals to the f times the delta, and the du equals to f dot the delta equals to r theta, right? Because it's an elastic deflection. So this delta is small, okay? It's quite small. So therefore, can say the delta equals to r theta. Okay? And the f r equals to the moment, right? The moment. Therefore, the theta equals to the partial u, partial m. Okay, the partial u and the partial m. Okay, this is the concept of the Cartesian theory. Okay. Okay, so that's we can quickly recap every loading applied, right? So this is for the actual loading, right? We got its the energy type, and then we can energy divided, the energy take the derivative with respect to F, we can get its deflection. Okay, and we know it's energy. And we know it's energy. Okay. Okay, and similarly for the direct shear, right? It's the energy. For the torsion, this is its energy. Okay, this is energy. Okay, and for bending, this is its energy for bending. Okay, for bending. Right? I'm gonna skip this process. I think it's not difficult to figure out what's this energy from the bending loading. Okay. Okay, and finally we got the energy for the transverse shear with the shape vector, or say the correlation factor. Okay, depends on the different cross section. Okay, different cross section of these parts or components. Okay. Okay, so this is one example for the Cartesian theory. Suppose we have the beam with the central loading P, right? And this cross section is the rectangular with the dimension B times H. Okay, first compute the energy and then partial derivative to get the deflection. Okay, and in this case, there are two types of loading, right? One is bending and shear. and the shear. Okay, and the magnitude of the bending at any position of x, m equals to the p over 2 times x, and the shear equals to the p over 2. Okay, in this case, we have two types of loading, bending and shear. Therefore, we have to figure out what is the energy for bending and what is the energy for shear, right? So I already mentioned this previously. We got its energy for bending, and also we got its energy for shear. Okay. And what's next? Right? So you can get the energy, right? Bending and shear, right? This is total energy, and we can figure out what this energy is, and we take the derivative. We take the derivative of the energy with respect to the force P, and we got a deflection. Okay. Okay. And the second method is we can just take the derivative first and then integrate. Okay, we take the derivative, partial derivative with the m with respect to the force P. Okay, and then we take the integration. Okay, and this part is for bending, and the second term is for the transverse shear. Okay, transfer. This is for the bending and for the shear. Okay. So for this second method, we can directly get the deflection. It's the differentiate under integral. And the first method is the differentiate after integral. Okay, so I'm just gonna recall your memory. Okay, just want to recall your memory. Okay. Okay, so let's go back to the helical spring. Okay, let's go back to the helical spring. Okay, so I already mentioned that previously for the helical spring, we have two energy, right? One energy from torsion, right? And the other energy from shear, direct shear, right? Direct shear. And then we already know the energy for bending, energy for shear. Okay, and we substitute those values of the torque, length, and the polar moment, and the cross section, right? And we got the total energy for the helical compression spring. And therefore the deflection for this compression spring, we just need to take the partial derivative of the energy with respect to the compressive force, right? Compressive force. Okay. And finally, we get the deflection. Deflection equals to this term. Okay. And the terms of the C over 2C square approach to zero. Okay, approach to zero. Okay. Approach to zero. Because as what I mentioned previously, the C, the spring index is between 4 to 12, right? It can be between this number, okay? It can be 5, 6, 7, 8, 10, 12, 11, and so on, and so on. So no matter what, the C square times 2, and this term we are close to 0 compared to unity. Therefore, we can ignore this term, except for the low C value. Suppose this C is, let's say, 2. C equals to 3. Okay, in this case, maybe you have to take into account this term, okay? But in general case, these terms can be set to 0. Okay, therefore the deflection equals to this term, right? Or equals to this term. Okay. And then we can define the spring rate or spring constant K. Okay, and then we can define a spring constant or spring rate. Okay. Because F equals to a y, right? Okay, so for the different end condition, you can define the different number of coil or the number of active coil. Okay, so for example, the pen end and the right hand rule, right? For the right hand springs, in this case, there's two end we define as the plain end. Okay, the A, and for the B, one end is square, or we say it's closed. One end is closed, the other is plain. Okay, the C case is square and grounded. It's been grounded. It has been grounded. Okay, has been grounded. And for the D is plain end and grounded left hand. Okay, so this left hand. It's different direction to wire. Okay, to wire this spring. Okay, spring wire. Okay. Okay, so we can define the total number of coil NT, right? The number of active coil NA, and the solid length. The solid length equals to the NT, the total length times the wire diameter plus the wire diameter, right? This is the total number of the coil times the wire diameter, right? And plus the extra coil wire diameter. Okay. Okay. And the free length can be defined as the L naught is a function of the pitch and A and the wire diameter and the wire diameter. Okay, and there is a table to list all those the coil evaluated by the end condition, based on the end condition. Okay, so for this plain end, okay, for this plain end, the end coil equals to 0, and the total coil equals to the active coil number, okay, and the free length equals to the pitch, P times the NA, the active coil diameter plus the wire diameter, and the solid length, okay, and the pitch, okay, and so on. For the plain and the ground end, the end coil equals to 1. For the squared and the closed end, the end coil equals to 2. Okay, so we can, from this table, we can decide this NA, NT, L naught, LS, okay, based on the end condition. Okay, based on the end condition from this table. Okay, from this table. Okay, so I'm gonna stop here. So we're gonna go into the other section as called set removal or presetting, which is a process used in manufacturing a spring to induce the use for residual stress. Okay, so this is the different section. Okay, so we're going to introduce the different residual stress inside the helical spring. So I'm going to stop here. Okay, I'm going to stop here, and therefore you can just pre-study this section.